Welcome back to this course, Advanced Memory Hierarchy Design. The topic of this lesson is techniques to reduce the cache hit time. As usual, the source of this lesson. It is based on section 2.2 of the textbook. Some parts have been based on other sources or on earlier editions of the textbook, since some techniques that were present in earlier editions have been removed from the 5th edition. In the first lesson of this course, I presented the equation for the average memory access time given by hit time plus miss rate times miss penalty. So we immediately see that we can improve the AMAT by either reducing the hit time, the miss rate and/or the miss penalty. Unfortunately, improving one of these terms often negatively affects the other terms, so a trade-off needs to be made. In this lesson, I will focus on techniques that reduce the hit time and the miss penalty. There are also techniques that cannot be easily classified as reducing the hit time, miss rate or miss penalties. These are techniques that increase the cache bandwidth or that reduce the miss rate or miss penalty via prefetching. I will discuss these techniques in separate lessons. The first technique I want to discuss is way prediction. Before I do so, however, let me try to give a short motivation. This figure shows a 4-way set associative cache. We would like to employ a set associative cache because it typically has lower miss rates than a direct map cache. Unfortunately, set associative caches have a longer hit time than direct map caches, mainly because a multiplexer is needed to select the right data word. In a direct map cache, the data can be sent to the CPU while the tag comparison is being performed. In a set associative cache, the tag comparison has to take place before the data is sent to the CPU to select the right data. The question now is, how can we combine the fast hit time of a direct map cache with the lower miss rate of a set associative cache to achieve the best of both worlds? One such technique is way prediction. In this technique, there is an extra table that is used to predict the way or block within the set of the cache access. In other words, in which way of the cache do we expect to find the block? This allows setting the multiplexer early to select the desired block, and if the block is found in the predicted way, only a single tag comparison has been performed. If the prediction was incorrect, we need to check the other blocks in the set. I read the original way prediction paper because I wanted to explain you in detail how it works, but found that it takes more than a few slides to do so. Very briefly, the way prediction table can be indexed by some bits of the program counter or the value contained in the base register exclusively ORed with the offset. The advantage of using the PC is that it is available very early in the pipeline, but it can't distinguish between two executions of the same load accessing different cache ways. The base register value XORed with the offset can, but it is available relatively late in the pipeline, but still before the effective address. Anyhow, way prediction has been used in the Alpha 21264 processor, and the prediction table has been integrated into the instruction cache with 1 bit per cache block. If the predictor was correct, then the hit time was 1 clock cycle and 3 if not. Furthermore, the prediction accuracy was about 85%. It was also used in the MIPS 4300 embedded processor to reduce the power consumption. Way prediction reduces the power consumption because in most cases only one way needs to be activated. Way prediction is also used in the ARM Cortex-A8 with 4-way set associative caches. One problem with way prediction is that now we can have a fast hit or a slow hit. If the prediction was correct, then we have a fast hit as shown here on the left. If the prediction was incorrect, then we need to activate the other ways. If we find the requested block in one of the other ways, we have a slow hit or pseudo hit as shown here on the right. When the requested block is also not present in the other ways, we have a miss and incur the full miss penalty. The second technique I want to discuss is column associative caches. The motivation for it is actually the same as for way prediction. How do we combine the faster hit time of direct map caches with the lower miss rate of set associative caches? A column associative cache is actually a direct map cache that is considered as consisting of two independent halves. First, the cache is accessed using the usual index, and if there is a hit, we're happy and return the data to the CPU. If there is a miss, we access the cache again, but with the highest index bit inverted. So we now access the other half of the cache. If now there is a hit, we're still happy and return the data to the CPU. If there is a miss, we fetch the block from the next cache level. In both cases, we swap the two cache blocks so that when the CPU accesses the same block again, it will hit on the first access. This figure illustrates what happened. In the first access or the first probe, the cache is accessed using the normal index. When there is a miss, we access the other half of the cache and swap the two blocks. In this example, I assume that the highest index bit is inverted, but we can, in fact, use arbitrary hash functions for the first and second probe. For example, we can also invert the lowest index bit. The motivation for the third cache optimization is again similar. How do we get the fast hit time of direct map caches but avoid the large number of conflict misses that typically occur if there is no associativity? The victim cache solution is to add a small but fully associative cache between the level 1 and the level 2 caches. This cache buffers blocks evicted from the direct mapped level 1 cache in case they are needed again soon. The victim cache was proposed by Norman Juppy in 1990, and he showed that a fully associative victim cache consisting of only 4 blocks removed 20% to 95% of all conflict misses for a 4 kilobyte direct map data cache. 4 kilobyte is of course very small compared to present day standards, but the programs and datasets were also much smaller at that time. The victim cache has been implemented in alpha processors from HP, and the AMD Athlon processor had a victim cache with 8 entries. The victim cache may be accessed in parallel with the primary level 1 cache or sequentially, one after the other. Let's assume they are accessed sequentially. Then we first do a lookup in the primary cache, and if it hits, we simply return the data to the CPU. Otherwise, we have a miss in the primary cache. We do a lookup in the victim cache. If it hits there, we return the data to the CPU and we swap the cache line in the victim cache with the cache line in the primary cache, so that the next time this block is requested, it will hit in the primary cache. If the block is also not found in the victim cache, we need to fetch the missing block from the next cache level or main memory into the primary cache. Furthermore, the block that is replaced from the primary cache is moved to the victim cache. I would also like to remark that there is no fundamental reason why the victim cache should be fully associative, but usually it is because the attempt is to avoid conflicts. The underlying idea is that the victim cache should be very small, and if it's not fully associative, there will be many conflicts in the victim cache. Finally, I would like to remark that while I presented the victim cache as a hit time reduction technique, it can also be classified as a miss rate or miss penalty reduction technique. It can be classified as a miss rate reduction technique since the aggregate miss rate of the primary direct map cache and the victim cache will be smaller than the miss rate of the direct map cache alone. It can be classified as a miss penalty reduction technique because the miss penalty will be lower when there is a miss in the primary cache but a hit in the victim cache. This completes this lesson. Thank you for watching. In the next lesson, I will describe techniques to reduce the cache miss penalty, which is another component of the average memory access time. Hope to see you back.